Hello students, today I am going to give some properties of cancellation laws and integral domain in this lecture. So first of all, I would like to start with properties. What are the learning objectives of this lecture? The objectives of this lecture is to understand the properties of cancellation laws and integral domain. So that first I shall see that properties of this integral a ring. A ring R has no zero divisor if and only if cancellation law holds good. Cancellation law holds in that ring R. Suppose the cancellation law holds in R, that is A dot B equal to A dot C is if we have a left cancellation law, so that which implies B equal to C. So now we take a non-zero element A such that A dot B equal to 0 for all A comma B are the members of R. Since A dot 0 is 0, as we know the property is this. So thus, A dot 0 equal to A dot B. By cancellation law, again this A gets cancelled each other by left cancellation law. That implies B equal to 0. Thus, we have that is A is non-zero, then B is 0. That implies B equal to 0. Thus, R has no zero divisor. Then, conversely, we have that if R has no zero divisor, we assume that this R has no zero divisor. That is, for A dot B is 0, either A is 0 or B is 0, not both are 0 there. Suppose for A is non-zero, as we have proved that AB equal to AC, that means AB, just if you take this side, AB minus BC, that is AB equal to, that is what here it is AB equal to BC there. So AB minus BC, just we can take this side, it becomes what is that? It is AB minus BC. So then we have there, so that by taking A on both sides, so that it becomes what here? B minus C, this implies that. So since R has no zero divisor and since A is non-zero, so that means B minus C equal to 0, which implies B equal to C. This shows that the cancellation law holds in that R. So next we shall see the properties of integral domain. So as we know that field concept, so that every field F is an integral domain. So what we shall prove here that F is an integral domain. So since F is a field which is commutative ring with a unity, therefore in order to show that every field is an integral domain, we should also show that a field has no zero divisor. As we know that it has its every field has no zero divisor, since because this is the concept of field, but it has multiplicative inverse there. So but which has no zero divisor. So we should show that here a field has no zero divisor. So let us take for all A comma B are the members of F. It is field. With field is also part of that ring there. So with A element A is non-zero, such that A dot B is 0. Since A is non-zero, inverse exists also in that field. Therefore, multiplicative inverse or inverse exist in that. So now, therefore, A dot B equal to 0, That means multiplying both sides by A inverse, so that A inverse into AB equal to A inverse dot 0. Therefore, by associative property, so that A inverse A into B equal to 0 there. A inverse A is unity, that there is a inverse element property, so that that means it is A inverse, since A inverse A is 1, so that is 1 into B equal to 0. That means B is 0 there. And now similarly you can take it A dot B is 0 and with B is non-zero. So we cannot take it both simultaneously, B non-zero, A non-zero. So that one by one we have to see that here. So that in previous, that is A non-zero and A dot B is 0. So that A dot B equal to 0 there. And here, since B is non-zero, inverse of B is also exist in that field. And therefore, A dot B equal to 0, just multiplying on the right side of that right side of this A dot B and this 0 dot B inverse. So that is what AB into B inverse equal to 0 dot B inverse. A dot of B into B inverse equal to 0. There, since associative property holds good. So B into B inverse there. B, as we know that inverse element property, so that B into B inverse is 1. So that we have that A dot 1 equal to 0. So that means A equal to 0. This is an identity element also. There is exist inverse element property also. So that's why, so that is, if we have that A dot B equal to 0 with B is non-zero, that implies A is 0. So this is what we have. Thus, in a field F, we have also that A dot B equal to 0, that implies either A is 0 or B is 0. Therefore, a field F has no zero divisors. We have field F is a commutative ring with the unity, because it has exist also unity element. So, and also no zero divisor. Therefore, F is an integral domain. So this what that. And next property of integral domain, every finite integral domain is a field. But every field is an integral domain, but not every field is every integral domain is a field. Only we can have that property here. Every finite integral domain is a field. So now let us see that proof of this property, every finite integral domain is a field. Let us take a T be a finite integral domain. So we have elements of this D, which contains the finite element here. So then we show that this dP is a field. That is, we have to show that every that integral domain has a unity, that is unit element in that. So that one is the element of D there, or it is a member of that. And also property condition for this integral domain. So every non-zero element of D has its multiplicative inverse in that domain D. So now let us take every non-zero element. So when we take that is the element which is non-zero, that is A is non-zero, which is the element of D. Now we form the product of this here, it's non-zero element. So x1 dot x1a comma x2a and so on x and a, that. So which is a product that. Since D is closed under multiplication, thus these are all elements in that product, x1a, x2a, x3a and so on xn a, which are the members of D there. That is D is the integral domain. So that is what that means, which are the members of that. So that ultimately which contains in D that. So now we will show that all these elements are distinct elements. So if possible, we prove that let xi a equal to xa a, where I is not equal to j there. Possibility we can have, that is if possible. So xia equal to xja. That means so that I is different from j. So that if that case, so that we can take this xia and xj this side, it is minus, and a with this here, that equal to 0. Since D is an integral domain, thus we have no zero divisors. It has no zero divisor. Either this xi minus xj equal to 0 or a is 0. So suppose a is non-zero, so xi minus xj equal to 0. That implies xi equal to xj. This shows that all the elements are distinct elements here. So because since xi is not xi equal to xj, but I is different from j there. So this shows that all the elements are distinct, and which is equal to d there. So then now let us take y is a non-zero element of D, then y equal to xia. So that let us take that is xia is, that is the is y for some I there. So now we have that this a is member of a D, then a equal to xja also for some j. So therefore that you can have a you can replace it by here xja there, xi into xja, so that, or since it is commutative property, a xj there, since D is a commutative ring. So this D is an integral domain, is a commutative ring. That's why we can write it like this, xja by a xj, or xia into xj. That means xia is y. This is what y xj there. This is possible only if xj is 1 there. So thus it has unit element in D there. So since that this D has unit element, then there exists a non-zero element B, also member of D, such that B dot A is 1. That implies B is the multiplicative inverse of A. Hence D is a field. So every finite integral domain is a field. So as we have seen in the previous property, every integral domain is a field, but every field is an integral domain, but every finite integral domain is a field. So that now we have a corollary of this here. If phi is prime, then the set ZP is a field. That means what? As we know that integer system phi with the prime numbers is a field. So now we shall prove this result by taking as ZP is, that is 0, 1, 2, etc. p minus, to show that this ZP is a field. That is, we have to show that ZP is an integral domain. That is, it has no zero divisors. For this, we can take it A complement, B complement, which are the members of ZP. Means that these are the members of ZP here. So, and also let A complement dot B complement is 0. Since this A dot B, A complement dot B complement, which is divisible by P, that prime number, because P is prime. So that means either this A is divisible by P or this B complement is divisible by P. So all that means which are these two are the members of ZP there. So if A is divisible, P is divisor of A, then A complement is 0 mod P there. Or else if P is divisor of P complement, then P is 0 complement of mod P. Thus ZP has no zero divisor. Therefore ZP is an integral domain. ZP which contains the prime numbers. That since ZP is a finite, therefore ZP is field. So next property we are seeing that last property. So a commutative ring R is an integral domain if and only if cancellation law also holds good in it with respect